Hello. So I briefly talk about this fresh archive about Wheeler-Feynman theory, which is very symmetric in emission, but from perspective of asymmetry of radiation, there is required asymmetry for gravitational waves. So let us briefly look at the first diagram, so here we have two orbiting masses, like black holes, and they are emitting, it is assumed we observe them, they are emitting these gravitational waves, the ripples in space-time. So, but this is very symmetric situation. So we could evolve it forward in time, but we could also evolve it, switch time, and then evolve it. So in both views, they are just orbiting or masses. So here they are emit waves. So why not also here in this perspective? So this is called generally the Wheeler-Feynman absorber theorem, that we should have both the retarded wave later, but also the advanced wave, aerial. Yeah, so more or less, not exactly, but more or less, both chips should have similar shapes for this spiraling they see in LIGO. So in theory, LIGO could see both the standard retarded, but also why it shouldn't also see the advanced wave. Yeah, so not exactly, but with a closed chip. So the question is, so LIGO just measures length. So in theory, it should be able to see both. The question is, are they created also those? So in Wheeler-Feynman, there is assumed that they both have the same contributions. There is one half contributions of both. However, for example, the spiraling, they are not just orbiting, they spiral losing energy. So it says that the retarded waves are dominating. So there is asymmetry. Yeah. So this is this asymmetry of radiation, which is crucial here, which is missing, I believe, in the Euler-Lagrange. So the standard assumption is that the asymmetry is perfect, that there are only the retarded waves, but maybe there is also a small contribution of the advanced wave. So this is a hypothesis uh, I I propose to test and I will discuss. And there are many experimental arguments that maybe are already among them observations. There are like 400 of them currently. Maybe there are some advanced waves. Yes, because the chip shape should be quite similar. So ultimate way to confirm they were retarded wave is the electromagnetic counterpart, which usually is retarded. So, however, there is only observed one of them. Yes, so the big question is why we don't see more. So most of them there are black hole mergers, but there are also like 10 mergers, including neutron stars, which generally should be seen. So maybe it's worth to consider, especially in future when there will be lots of such events, that some of them were advanced wave. Yeah, so if we are certain that there should be some visual also this electromagnetic counterpart, but clearly there isn't, we are certain that it's not, then it might be the only options to assume it was advanced wave. Another type of argument, there are two early events so like this merger of two black holes of 66 and 85 solar masses. So there are in so-called black hole mass gap. So in theory, they couldn't get directly from collapse. So to get them, we need some hierarchical merger. So, but it needs time, and now this time was spent both for the first and for the second. So this is an event which requires, in theory, a lot of time, but it's observed like I think 7 billion years ago. So it seems too early to happen. So it's very low probability. Seems very low probability that it has happened so early. So maybe we should consider the alternative explanation that it was not earlier but later. Maybe it was advanced event. Another type of argument is there is this so-called pulsar timing arrays. They call it vibrations of the universe, and they say so there are extremely low frequencies that they say they require orbiting supermassive black holes, but according to current knowledge, they are not enough these supermassive black holes. So you considering only the retarded ones, it seems insufficient. So maybe you should also include the advanced one. So if you think about space-time as a 4D membrane, when there is some perturbation, the circulation, it should both emit waves forward, but also maybe backward in time. So symmetry suggests that there should be both. Yeah, so there are these various types of arguments. They should be tested. It's quite difficult. I'm looking for a collaboration to make it more serious. This is a very initial article just to show that maybe it's too early that we have we said that only retarded waves are there. Yes, so maybe the contributions of advance is not non-zero. Yes. So that we should not, instead of assuming it, we should test it, try to estimate this asymmetric coefficient. I called alpha here. So why we can, so if the equations are symmetric, the asymmetric has to go from the solution. So the boundary conditions are asymmetric, making that not the amount of advanced and retarded waves, this is not symmetric. There is definitely more of those than those. The question is if there are non-zero amount of those. Yeah. So the asymmetry has to have to come from the boundary conditions, and the boundary conditions, I think the simplest are by just if there are emitters absorbers. Yeah, so now there are definitely more absorbers in our future than emitters in our past. In far future, they might be reversed. And in between, let's say, Big Bang and Big Crunch in the middle, there could be balance. That rotating mass or charge could not lose energy, would just emit and absorb the same amount, and this would be the Wheeler-Feynman condition. So maybe it will be reached in some future, but now there is asymmetry because there is more absorbers than emitters, but this is not perfect. So why? Sure, there are more absorbers, but the number of emitters is not non-zero. So maybe this alpha should not be assumed zero as currently is, but maybe some small, let's say 100s, 1000s uh, amount, which says that there should be also the advanced wave, but they should be weaker. And so why I'm talking about the gravitational wave? So because the LIGO just measures length changes, which are basically time invariant. So it doesn't matter if there are advanced or retarded wave for LIGO. However, for electromagnetic waves, it's much more complicated because if you think about, let's say here is a black hole, a white hole, it emits photons, and now we observe our receiver absorbs this wave as retarded by absorbing. Yes, it excites this resonator inside this telescope. But however, for advance, we need to apply time symmetry to this scenario. So we replace this white hole with black hole, and now it de-excites, it absorbs photon, and now it stimulates emission in our telescope. And now this simulated emission would be advanced wave. However, to make it happen, we would need to excite this telescope initially, which is much more difficult because usually the telescopes are cooled, so we avoid this effect. While if you would like to see advanced wave, you would need a kind of special, at least amplifiers for telescopes to make it excited, maybe at least thermally excited. So maybe it's possible, but we would need to modify our radio telescope. For current situation, we can use the gravitational wave data, but for electromagnetic, it needs at least modification. Yes, so to imagine this situation, I think this hydrodynamical analysis is very nice for intuitions. So having this marine propeller, and it creates wave carrying energy, momentum, angular momentum. So this is very similar to photon. It can excite target. But we can practically apply time symmetry by just rotating the opposite direction. Yeah, so it's relatively trivial for marine propeller, just change the rotation direction. And now instead of pushing, we reverse both the angular momentum and momentum. Instead of pushing, we pull. And if you hit excited resonator, it could pull energy from excited resonator. Yes, and it should be the same here, that the black hole should also actively pull electromagnetically with negative radiation pressure, acting with stimulated emission equation on the target. Okay, so maybe very briefly, let's look at the equations. So here are the standard, here are the Maxwell equations in the most compact form. which have this solution, and but due to symmetry, there are two types of solution: the retarded and advanced solution. Yeah, so it's plus or minus in time. So in Wheeler-Feynman, there is assumed there is one half, that both should have one half contributions. However, in theory, they are allowed any convex combination. So maybe we shouldn't choose. So one half is definitely wrong because of inspiraling. Yeah, so it loses energy. So definitely the retarded is stronger, but the question is if the advance is zero. Yeah, so I introduced this let's say alpha, which defines this like here, let's say that it should be very small, let's say 100s, 1000s maybe, and it should be evaluated from parameters. And for gravity, we have very similar. The equations for linearized gravity, the equations are very similar. Sure, for mergers, finally, it should be more complicated. Yeah, so this is very initial article. So a lot of questions just asked, and hopefully we can estimate this alpha instead of assuming that maybe it's non-zero, this advanced term. So how to estimate it? So there are many ways. So for example, you could use this alpha, include it in some cosmological models, and check if so for zero we get the standard view. If you could check if using non-zero we can improve the agreement of the model. Or the best would be in the direct testing, that we have some object which we can be certain that it's advanced. For example, that if you are certain that it should have electromagnetic counterpart, but we are also certain that it doesn't have this counterpart. Yeah, so in this case, I think the only options is that it was advanced event. So having these events advanced and retarded, we could check the luminosity, and by dividing them, hopefully you should be able to estimate this alpha. Yeah, so there are some ways. So there are some new ideas, new views, and I hope to find some collaboration to make it further. Okay, so thank you for the attention.